1996 AB1, we're given the graph of f prime, the derivative of a function f, and the domain of f, the original function, is a set of all real numbers x such that x is greater than -3 and less than 5. Now I would just make a note that we're working with an open interval here. Usually when we're working with a derivative, we will be working with an open interval because most of the theorems and the ideas in calculus require that we have a function that's continuous on a closed interval and differentiable on an open interval. And since this is the derivative, we're showing that the function is differentiable on the open interval. Now, when a function is differentiable, it implies that it's also continuous. So we are working with a continuous function. F is continuous. And although we don't know the values of the endpoints at this point, we do know that the function is differentiable everywhere in between the endpoints, which is important. So let's get started. For what values of x does f have a relative maximum and why? And I state that f of x has a relative max when f prime of x changes from positive to negative. This always occurs at a critical value, in this case at x equals -2. Remembering what a critical value is, it's a place where the derivative is 0, the first derivative is 0, or does not exist. So everywhere in this particular graph of f prime exists everywhere, and it is 0 only at 3 places: at x equals -2, at x equals 1, and at x equals 4. However, in only one of these 3 instances does the derivative change from positive to negative. Second question, for what values of x does f have a relative minimum and why? I answer, f of x has a relative minimum when f prime of x changes from negative to positive. This always occurs at a critical value, in this case at x equals 4. So it's almost the same exact answer, only we're working with a relative minimum, and that will occur when the derivative, first derivative, changes from negative to positive. And in this case, it has to be at one of the critical values, that is where the function is either 0, the derivative is 0, or doesn't exist. There were 3 of them, remember: x equals -2, x equals 1, and x equals 4. But we're looking for the specific instance where the derivative changes from negative to positive, and that's at x equals 4. Alright, we're moving right along. C. On what intervals of the graph is the function concave up? I'll scroll up a little bit. Use f prime to justify your answer. Well, we know that a function is concave up when its second derivative is positive, greater than 0. But we don't have the second derivative in this case. We do have the first derivative, and we're asked to use the first derivative to justify our answer. Well, if you remember that the first derivative tells us when the original function is increasing or decreasing. So when the original function is increasing, the first derivative will be positive. Or when the first derivative is positive, the original function is increasing. Now, if we work backwards from the second derivative, well, when the second derivative is positive, it tells us that the first derivative is increasing. Just like when the first derivative is positive, the original function is increasing. When the second derivative is positive, the first derivative is increasing. So all we really have to do is find where the first derivative is increasing, and that will tell us where the second derivative is positive, and hence where the original function is concave up. And in this case it happens between -1 and +1, and from 3 to 5. And that's all that we have to state there. So we know when the first derivative is concave up that when the original function is concave up, the second derivative will be positive and the first derivative will be increasing. And we'll go on to part D in the next video.